Are you able to see the slide?
Yes, sir.
Okay. So we have already discussed about the iteration method, Newton-Raphson method, and I don't know whether I have told that or not, that iteration method will be slower method. It is of order 1 method. Newton-Raphson method for vector case, that is also quadratic convergence it has. I have already explained how to derive the Newton's method for the vector case or the uh, more than one system of equations, nonlinear equations are there. So we'll see demonstration through one example of both the things, that iteration method as well as here Newton-Raphson method. That will be applied once the differential equation is discretized, and once you see in the form of certain number of nonlinear equations, and then we'll apply either iteration method or Newton-Raphson. Newton-Raphson method is the faster one, so we'll see the demonstration for both. So here is one example, that is u double prime equal to 3 by 2 u square, u0 is 4, u1 is 1, the boundary conditions, and let us take h equal to 1 by 3, domain is 0 to 1, so it is 0, 1 by 3, 2 by 3 and 3 by 3, that is your 1. And at 0 and at x3 both the values are known. Your u0 is 4, u3 is your 1, and the how we'll discretize, we'll multiply h square on the both hand sides and then write the central difference approximation for u double prime. So h square uj double prime at a general point uj equals h square 3 by 2 uj square. This is a non-linear term in the differential equation. So you know that the second order approximation for h square uj double prime is your minus uj minus 1 plus uj 2 uj minus uj plus 1, and then equals your minus h or 3 by 2 h square uj square, that is the nonlinear part is there. So that h is 1 by 3, so it will be 1 by 9, so it will be 3 into 2, so that is 1 by minus 1 by 6. So that's the reason it is minus 1 by 6. uj square is written. So now we'll write this for j equal to 1, j equal, because we require for j equal to 1, 2 and other things, 3 it will be automatically there. So for j equal to 1, we'll get that minus u0 plus 2 u1 minus u2, and then equal to your minus 1 by 6 u1 is square. Rewrite it in the appropriate, because u0 is known to you, u0 is given as 4, so this will take on the other side. So this is your 2 u1 minus u2 equal to minus 1 by 6 u1 is square plus 4. This is the first equation. For j equal to 2, accordingly it will be minus, if you see this j equal to 2, so this will be your minus u1 plus 2 u2 minus u3. u3 is your 1, so it will be taken on the other side. So basically it will be your minus u1 plus 2 u2, u3 will be on the other side, 1 by minus 1 by 6 u2 square plus 1. If we want to apply, so there are two equations we have, basically two nonlinear equations, 1 and 2. So if you want to apply this, and this is in u1 and u2, you want to apply the iteration method. So we'll write this r plus 1th part just like your Picard's one, that r plus 1th value on the left hand side. That's the reason I have done in such a way. So minus 1 by 6 u1 rth value. So once rth value of this non-linear part is, which is already known, for example r equal to 0 if you take, so this will be u1 u11 minus u21 equal to 1 minus 1 by 6 u10, but u10 is already in your hand. So this you can start with plus 4, and similarly your the other equation, the second equation is also written in terms of iterative form, that is u1 r plus 1 plus 2u2 r plus 1 equal to 1 minus 1 by 6. The nonlinear part is written as at r. So the evaluation will be done at the previous stage and then plus 1. So these are the two equations you'll get in your now it is linearized. Once it is the previous value, so this is known. This u1r, u2r, both are known quantities. So we may write in terms of your matrix equation. This is the coefficient matrix A, that is your 2 minus 1 minus 1 2 u1r plus 1 u2r plus 1, and on the other side this is known. So now this is in the form of Ax equal to B, and now you can use your Gauss elimination LU decomposition. Here it is 2 by 2 only, but if it is more, obviously for your own problem it will be more, number of the size will be more, and then you can use your Gauss elimination or LU decomposition or anything of that kind. Now, let us take the initial guess for U1 and U2 as 2 and 1.5. This is the another thing which you have to choose. The initial guess, this is one of the major part. And how to choose, maybe I may explain a little later. So U10 let us take as 2 and U20 is 1.5, which will be given to you. And now once you have this, then you can write down, for example, U11 will U11, U21. This on the other side, this will be U10 and U20. That two values are required. So this is 2 and 1.5. Put these values here, and you get that the things here. On the right hand side, everything is known. On the left hand side, this is a simple equation, Ax equal to B type of thing. Solve this, and then you get the value U1 1, U2 1, and then proceed further. Once the first one is available, you can continue this till you require, till you get the, till you meet your tolerance. So, is this iteration method is clear to you people?
Yes, sir, but only that doubt.
Pardon me?
How to choose the initial guess?
That is a difficult job. It's not an easy job. So, for example, you have any, there are 2-3 ways which you can look into. One, either you know the problem well, in the sense that from where that problem has come, you have to see that physical system, whether it is possible to get some initial guess for the solution. Means you can draw the graph of those function and so on and so forth. That is also not always possible, because the problems which were framed from natural phenomena is a very difficult job to get some kind of approximation. Another very simple way is that for any problem, suppose y double prime equal to fx is given, f is your non-linear function, fxy rather I say. So you write down the Taylor expansion of fxy. The first term will be your a constant type of term. First term will be a constant type. If nothing is possible, that will be a very crude initial approximation. So you write down y double prime equal to that. I mean, for example, your domain starts from 0. So write down Taylor expansion at the point 0 and y0, and then you see that some constant will come, the very first term. The second term will have the other derivatives and so on and so forth. So if it is possible to somehow linearize this fxy on the right hand side, which is a non-linear term. So, and then, for example, suppose we get that y double prime equal to k, the constant k. You solve this linear differential equation with the given boundary condition, whatever the boundary conditions were given. So whatever the solution you get, That will be one of the initial guess. If it is possible to get the next terms, you will get a little closer one. Getting next term is not at all a problem. Problem is that once you get that next term, for example, suppose y double prime plus k equal to k plus let us say that even a constant k L into your y is there. Even this problem you may be able to solve. So solve this problem and then whatever the and then apply the boundary conditions. If it is possible to get the solution of this type of boundary condition, then you will be little closer and like that. So if you proceed this way, you can try your initial guess closer and closer up to whatever extent you can solve that linear differential equation which you are getting from the non-linear differential equation. Is this clear to everybody?
Yes, sir.
Okay. So there are several ways. I mean, somehow one has to get that, but it is really very difficult job for any problem. It is very difficult job. So one tries to linearize the non-linear term somehow to the nearest linear part, and then try to use something. But linearization linearization is not at all problem. Problem is after that getting the solution of the linearized equation which you have got from your nonlinear equation. If it is possible to get, then it's fine. You can proceed with that, and then next value, if it is the faster method is there, for example, this Newton-Raphson, then the convergence will be faster. If it is your iterative method, it is first order, so it will be slow. Shall we proceed further?
Yes, sir.
Same problem I will solve using your Newton-Raphson method. I have already told how to solve. I'm just reminding that the Newton-Raphson method for the single equation xn plus 1 equal to xn minus fxn by f prime xn. Is that right?
Yes, sir.
Okay. So let us write the vector xn plus 1. This will have the x1, x2, x3, the n components are there, equal to xn, and then how we'll write? Do you remember that? How this derivative is replaced there?
Yes, sir. It was done last class.
It was replaced by? It was replaced by Jacobian. It was replaced by, or shall I show again?
No, sir.
Is it, do you remember that?
Yes, sir. We have to visit just.
Okay, okay. So let us come back to those two equations which we have just got there, the two discretized equations. So the same problem, u double prime equal to 3 by 2 u square, u0 is 4, u1 is 1, h is 1 by 3, same, everything is same. And then 1 and 2 is written here, then 1 prime and 2 primes are written there, right? Everything is written there. It is just multiplied by your 6. So it will be your minus 6 u1 plus 12 u2, and then minus u1 is square plus your 24. From where the 24 is coming?
The first equation is multiplied by 6.
Oh, that is first. Okay, so this is your 6 into that, 6 into 4, that is 24. And the second equation is your, you multiply by 6, so this is minus 6 u1 plus 12 u2 equal to minus u2 square plus 6. So this 1 prime and 2 prime is there, right? So the two non-linear equations which you get just like your fx equal to 0, here you will get f1 u1 u2 equal to 0, f2 u1 u2 equal to 0. Right?
Yes, sir.
Is that right? So Jacobian is nothing but it is del of f1 f2 with respect to u1 u2, meaning by del of f1 del of u1 del of f1 del of u2 del of f2 del of u1 del of f2 del of u2, exactly like 1 1 1 2 2 1 and 2 2, right?
Yes, sir.
Okay, then you have to calculate this del, and all these Jacobian is calculated at the previous value, right? So you'll see that. So del f by del u1, very obvious, del f by del u1, you just differentiate this with respect to u1, keeping u2 as constant, taking your u2 as constant. This will be 12, right? And then plus 2u1, rest, this u2 is there, this is constant term, so these two will not appear. Is that right?
Yes, sir.
And del f1 by del u2 means only minus 6. u2 is there, so you are differentiating with respect to u2, so that will be 1. Is that right?
Yes, sir.
Similarly, your del f2 by del u1, so this will be minus 6. These two terms are u2 terms, and then this is a constant sum, so nothing will come. And your del f2 by u2, this will be 2 u2 square, so that 2 u2 is coming, and then 12 into u2 is there, so u2 will go off, that will be 1. So 12 plus 2 u2. Is that right?
Yes, sir.
Okay, then your Jacobian is ready. Once your Jacobian is ready, the form of the Newton's method. Once it is a vector case, it is called the Newton's method. J into delta u1 delta u2. This is the increment in u1. This is the increment in u2, equal to exactly like your if you write that xn plus 1 minus xn, so that will be your delta xn equal to minus fxn. You may write that minus of 1 upon f prime xn into fxn. So this minus of 1 upon f prime xn is replaced by Jacobian. Is that right? If you see, if you take this Jacobian here, it will be minus 1 by j.
Yes, sir.
Right? I mean, that is not defined. The point is that I'm just trying to tell you that how you can remember the thing. So this you can rewrite as j into, I have already told that if you take this here, means it will be minus j inverse. Finding out inverse of a matrix on computer is a difficult job, very, very difficult job. And certain cases, this does not lead to your inverse at all. I mean, those matrices which are, it is not taught to you, those matrices which are quite sensitive, means lot of things are there. I mean, that will take more time. So there is one matrix which is very, very sensitive, that if you try to approximate that, I mean, using your computer, finding out the inverse, you will never reach. That is Hilbert type of matrices are there. Anyway, so that is not in your course. I'm not going to. So basically, I will write j into delta u1 delta u2 equal to my, so that you can apply your simple form is there. You can solve this for your delta u1 u2, and then you can proceed further. Now, this is your Jacobian. I have just written all the values we have already calculated, del f by del u1, del f1 by del u2, del f2 by del u1, and del f2 by del u2. So this is calculated. This is your Jacobian is written, del u1, del u2, right hand side is written. And then let us take the same initial guess, u1 0 as 2, u2 0 as 1.5. So you see, I have written u1 r, right? So this will be calculated at the previous value. So means for r equal to 0, we'll get that delta u1, and delta u2 means the increment for the next stage, and these values will be evaluated at 0, means u1 0, u2 0, will be put here, and then you see that once you put that, this is known, this is ax equal to b, because everything on the right hand side also it is evaluated at the previous value. So then you can find out your delta u1 and delta u2. Once your delta u1 and u2 is known, you can write down your next value of u1. So that will be your u11 will be u10, that is 2, plus whatever the value of delta u1 you have got delta u1, and then u20, which is 1.5, plus delta u2, that will be your new value, and then again you continue this process, so till you achieve your tolerance, and then you can stop at that stage once the both the values delta u1 and delta u2 are becoming getting repeated. Is that right? Just like your single variable Newton-Raphson. Is that right?
Yes, sir.
Okay. So is this clear that Newton's method? Further, it is not done.
Yes, sir.
So is this clear?
Yes, sir.
Okay, there is another thing. The assignment number 3 also I have uploaded here in the assignments. So you people can try those. Right? The submission date I will tell for all the 3.
Okay, sir.
It is I have already uploaded on this. There is one folder here that assignments.
Yes, sir.
Okay. So next I will move for another part. This is already done in the book, but let me tell that. Suppose, till now you have seen that fx y is there only if on the right hand side, means the problem is of this type, that y double prime equal to fx y prime is also there, then how will you proceed? So I will just close this file. Now that slide is, you can see the slide.
Yes, sir.
Okay. So you have already seen that 3 types of approximation we have seen for u prime, that is uj plus 1 minus uj minus 1 by 2h. This is of capital order h square. This is called the central difference approximation. Uj plus 1 minus uj by h, it is of capital order h. This is your forward one. Uj minus 1 by h. This is also capital order OH order, and this is your backward one, right? So we may use any one of them, depending. If it is possible to choose this one, so it's good. Otherwise, these two are there. But at the same time, the methods with the central one may not be stable. We'll talk about the stability after that. It may be stable with these two, forward and backward, even though this has only capital order H approximation, but it happens that. So let us see how we'll solve the problem. This problem is given in your book. So let us see that u double prime equal to u prime plus 1. So you have seen till now that y double prime equal to f type of thing. Here it is u double prime equal to f of x u prime also. Is that right? It may be in non-linear part also.
Yes, sir.
But that is not in your course, so I am not telling that. And the boundary conditions are given as u0 is 1, u1 is 2 into the exponential 1 minus 1. So we'll just discretize this. You know that the central difference approximation for this uj minus 1 minus 2 uj plus uj plus 1 equal to h square. If it is that's what I have said, that f x u and u prime in general. So it will be we'll write the central difference approximation for uj prime. You may write the forward difference approximation. You may write this backward difference approximation for uj prime. Any one of that you can use that. So let us use here that central one only, but the order of that will change accordingly. So h square uj prime plus 1, and uj prime is written as uj plus 1 minus uj minus 1 divided by 2h with the error of capital order h plus 1. Rewrite it. So the difference scheme is written as this. Is that right?
Yes, sir.
Is that right? Okay. So let us see the form how it looks like. So if h is 3, then x equal to 0, 1 by 3, 2 by 3, and 3 by 3, that is your 1. Means u naught is given, u3 is given, u naught is given as your 1, and u3 is given as 2 into e minus 1. So your scheme is ready. So write down for I equal to 1, j equal to 1. So it will be your 1 plus h by 2, h is 1 by 3, so it is 1 by 6 plus 1, so that is 7 by 6 is written here. J equal to 1, so it is u naught minus 2u1 plus, this will be 1 minus your h is 1 by 3 minus 1 by 6, so that is your 5 by 6, and this is u2, and so this should be j plus 1. Here there is an error. That it should be j plus 1. So make that, note down this correction. It should be j plus 1. The last term 1 minus h by 2, just check it. Whether it is plus. J minus 1 is there, j minus 1 and this h gets cancelled out. So h by 2
Yes, sir.
minus is here. So this becomes plus. So this is correct. So 1 plus h by 2 uj minus 1 and 1 minus h by 2 uj minus 1. Is that uj plus 1? Is that right?
Yes, sir.
So make this correct. Keep the, I mean, note down this. You have to make this correction. So for j equal to 1, this will become your 1 minus h by 2, that is your 5 by 6, I have already told, and then j plus 1 means it will be u2 equal to h square, h is 1 by 3, so it is 1 by 9, and similarly write down for j equal to your, so this is just rewritten, nothing else is there. Write down for j equal to 2, and then you solve these two, you get the values of your u naught is known to you, and u3 is known to you, and then so you can solve this for u1 and u2, means at the point 1 by 3, at the point 2 by 3. Just for demonstration it is taken only for two values, but for your own problem you have to take more number of domains. For example, h equal to 1 by 4, so this will be 0, 1 by 4, 2 by 4, 3 by 4, and this will be 4 by 4. So there will be three equations. If h equal to 1 by 6, accordingly the number of equations will change. Is that clear?
Yes, sir.
Okay. So just like your stability for your initial value problem, you have tested the stability for the problem that you have called as a test problem u prime equal to lambda y. Is that right?
Yes, sir.
Similarly, we will see here also the stability will check for u double prime plus k u prime equal to 0. U double prime plus k u prime equal to 0 on this, and we'll try to analyze the stability of certain methods, right? So I'm just closing this slide and go for further that your stability part. You just first find out the solution of u double prime. Write down the differential equation u double prime plus ku prime equal to 0. U double prime plus ku prime equal to 0. Everybody just find out the solution of this. How will you find out? A very simple equation.
It is a linear equation. E to the
So,
power dx. Integrated.
one way is that you may find out that auxiliary equation. Is that right?
Yes, sir, by d square.
D square plus kd equal to 0. And you can write down the general solution, or you just integrate it twice. Integrate it twice, you will get that. So there are two ways to proceed for that. Find out the solution quickly. The slide is, you can see the slide on your screen.
Yes, sir.
Okay. So find out this solution u double prime plus ku prime equal to 0. The roots are d equal to 0 and d equal to minus k. What is the auxiliary equation? D square plus kd equal to 0. Is that right?
Yes, I'm doing by nothing.
So this is, it is just one line. So this is your d into d plus k. So one solution is d equal to your 0, another is your d equal to minus k. So the general solution will be your u equal to a1 plus b1 into e to power minus kx. Is that right?
Yes, sir.
Or you can integrate it directly by writing du prime divided by u prime equal to minus k dx. Integrate once, you will get u prime by a constant b, and then again integrate it, the same thing you will get. So either you proceed auxiliary equation way, or you can proceed by integrating that. So you know that the exact solution is written as a1 plus b1 into e to power minus kx. Is that right?
Yes, sir.
Okay. Now, there are three differences schemes you have applied. One for the u prime, central. Second, forward. Third one is your backward one. So I have written all the three. So for u double prime, it is your uj plus 1 minus 2 uj plus uj minus 1 divided by h square. Since h square is not multiplied here, so that will be divided by h square plus k times uj plus 1 minus uj minus 1 divided by 2h, if we use central one. If we use the forward one, uj plus 1 minus uj by h. If we use the backward one, it will be uj minus 1 by h. Right?
Yes, sir.
Okay. Now let us proceed exactly like the way we have proceeded for your uh, first order differential initial value problem. So let us put uj equal to a into xi to power j in that 2, 3 and 4. That is your these two, 2, 3 and 4. Let us put first in 2 and see what is happening. So once we put into 2, we will get that it is your you are putting uj equal to, so put in this first one, uj equal to your write down uj equal to a into xi to power j.
Yes,
Put
sir.
that, simplify that. What you have done for your initial value problem first order, you have done that, you have divided by the minimum power of xi. So here you will get xi to power j plus 1, xi to power j, and xi to power j minus 1. So divide by xi to power j minus 1. See what characteristic equation you are getting. Do it quickly. You see, I have just put a into xi to power j. So first term was uj plus 1. So it is xi to power j plus 1 minus uj was there. So 2 xi to power j plus xi to uj minus 1. So xi to power j minus 1. Similarly, it is the central one. So xi to power j plus 1 minus xi to power j. The other coefficients are there. Divide by xi to power j minus 1. So we get a quadratic polynomial here, and rewrite that quadratic polynomial. So we have got this quadratic polynomial, and then you can simplify that. Xi minus 1 can be taken out. So finally we can see that xi minus 1 into this term is there equal to 0. Is that right?
Yes, sir.
Simple. The way you have done earlier also, that you have divided by the lowest power of xi, and then you get some polynomial one. So this is the same way we are getting the polynomial, the quadratic polynomial. Try to find out the solution of that. So it is written in that way: xi equal to 1. Either this is 0 or this is 0. So it will be xi equal to 1 or xi equal to 2 minus kh upon 2 plus kh. Is that right?
Yes, sir.
So it has the two solutions: a into xi to power 1, that is your uh, sorry a into 1 to power 1 to power j. So 1 to power j is your 1. So a1 plus b1 into 2 minus kh upon 2 plus kh to power j. Is that right?
Yes, sir.
The general solution.
Yes, sir.
Now we'll assume here, just for convenience, so that minus 1 to power j will not come, because if minus 1 to power j will come, then it will automatically oscillate. So to avoid that, we'll take that 2 minus kh is greater than 0. Whenever we require anything of this kind, we'll try to assume that type of condition. Is that right? Otherwise, automatically it will oscillate if minus 1 to power j will come, and that will depend on whether k is positive or k is negative or k is very large. So we'll
So
see the because k may be
particular,
positive, k may be, yes, hello,
so we are solving for particular range of k only.
we are doing for
Particular range of k by implying 2 minus kh greater than 0.
no, h is there, h is a known quantity, not the particular. Yeah, that will restrict our things, that will restrict our things. We
Yes, sir.
cannot go for any k, we cannot go for any k.
Yes, sir.
Once we assume that 2 minus kh should be greater than 0, depending on this k positive or negative, right? We will see that. Otherwise it always that minus 1 to power j will come, right?
Yes, sir.
So we cannot discuss the stability part. Now, just try to compare with the exact solution. What is the exact solution we have got? A plus b
A
into e to
plus
power
b into
minus
with k.
kx. Right? We are not putting any condition till now that k is greater than 0, less than 0, whatever it may be, accordingly that e power minus kx will behave. Right? Now, you see the constant term is in the, if you have solved this difference equation, then also this constant term is there, a1. There also a is there. So first solution is same. First solution is same. Is that right? Is that right?
Yes, sir.
Hello? The second solution here, it is 2 minus kh upon 2 plus kh to power j, while for the exact one it is e to power minus kx. If you put xj, then that will be minus e to power minus kxj. Is that right?
Yes, sir.
Now the point is that how close this term to your e to power minus kxj in terms of the behavior, right? So this is what will decide. This thing will decide about the stability of the particular method for the boundary for the second order boundary value problem. Is that right?
Yes, sir.
Okay, so this is what we have to see. So for this case, when we have this central difference approximation, so if you see that e to power minus kx for k greater than 0, this goes to 0 as x approaches to infinity. Is that right? The exact solution part.
Yes, sir.
Now we have to see this 2 minus kh upon 2 plus kh, if this is strictly less, whether this is strictly less than 1 or not. If we assume that part that 2 minus kh is always greater than 0, so that minus 1 to power j is not going to come in the picture. So this gives that condition on that k and h, k and h, that is kh should be less than 2 or h should be less than 2 by k. So depending on k, your h will be decided. K
Yes.
will be in the differential equation. H you are taking from your side. Is that right?
Yes, sir.
So this will be decided depending on the k given in the equation, in the differential equation. Now 2 minus kh upon 2 plus kh will always be less than 0 for k greater than 0. This will always be less than 1 for k greater than 0. Is that right?
Yes, sir.
Means what? Its power j will go to 0 as j approaches to infinity.
Yes, sir.
As j approaches to infinity, means the second part of the solution, either it is difference equation or the exact one, both behaves exactly in a similar fashion.
Yes, sir.
Means it is in this case the method is stable. In this case the method is stable. Is that right?
Yes, sir.
Provided your h should be less than 2 by k. Provided h should be less than 2 by k. Otherwise, it will starts oscillating this numerical solution part. Is that right?
Yes, sir.
Next is if k is less than 0. Let us take k is your minus p and p is greater than 0. Rewrite it. So this 2 minus kh upon 2 plus kh will be your 2 plus ph upon 2 minus ph, where p is greater than 0. And again, we'll assume that ph is strictly less than 2 or h is less than 2 by p. So that minus 1 to power j is not going to come in the picture. Now, if we see e to power minus kx, the exact part, for k less than 0, this blows up as x goes to infinity. Is that right? K is less than 0.
Yes, sir.
Now, we just try to see this one. 2 plus ph upon 2 minus ph to power j will also blows up because it is 2 plus ph. P is greater than 0. Blows up as j approaches to infinity. Is that right?
Yes, sir.
So both are behaving exactly in a similar fashion. So again, there is no trouble, right? Now, if k is very, very large, then we divide by k. So it is 2 by k minus h divided by 2 by k plus h. So immediately as k approaches to infinity, you see this goes to minus h upon h or minus 1. And that will be minus 1 to power j once you take the power j. And this oscillates always. Is that right?
Yes, sir.
So it is not computationally possible to proceed further. There is no way we can put that restriction of that type. Right? Is that right?
Yes, sir.
Okay. Next, we consider the next case. That is your forward one. So, and then again put uj exactly the similar way. Uj equal to a into xi to power j. Rewrite it. Divide by xi to power j minus 1. You get a quadratic polynomial. Solve that. You see that one solution is coming as xi equal to 1. Another is coming as xi equal to 1 upon kh. Right?
Yes, sir.
So one solution is always coming same as your exact solution. The second solution comes as 1 upon 1 plus kh to power j while there it is your e to power minus kx. Now we have to see whether the behavior of this term is similar to the exact solution part or not, right? Because one part is same for both. So similar way we'll just proceed. For k greater than 0, 1 plus kh is always greater than 1, or 1 upon 1 plus kh will be strictly less than 1, right? So immediately you see 1 upon 1 plus kh to power j goes to 0 as j approaches to infinity, and this similar behavior that e to power minus kx for k greater than 0 also has, that it goes to 0 as x approaches to infinity. Is that right?
Yes, sir.
So next we'll see that when k is less than 0, let us write k is your minus p is greater than 0, and then immediately you see that e to power minus ks blows up as x approaches to infinity in this case. And 1 plus kh we can write as 1 minus ph, or 1 upon 1 plus kh we write as 1 upon 1 minus ph. Let us assume that 1 minus ph is always greater than 0, that is ph is less than 1, or h is less than 1 by p, that minus 1 to power j should not come in the picture. And then you see 1 upon 1 plus, so this 1 by 1, 1 upon 1 minus ph will always be greater than 1, and then you can see that this blows up as j approaches to infinity, and then similar thing happens here also, means both the behavior of both the parts are same. Is that right?
Yes, sir.
Okay. So next we'll see if it is very large, but it is less than infinity, sorry, less than 0. So it goes to minus infinity instead of plus infinity. So in that case, this 1 upon 1 minus ph goes to 0 as p approaches to infinity. But if you see this e to power minus kx, that is your e to power px, and that grows up as your x goes to infinity, not p. Here it is written wrongly. P goes to infinity as x approaches to infinity, right? So again, the difference scheme is infeasible. Is that right? Is that right? The behavior of both the parts are not same. This is going to 0 while this blows up. Is that right?
Yes, sir.
So similarly, we will see the last case. That is your backward one. So again, we'll write that uj as a xi to power j in, and then try to solve that. We'll get a quadratic equation by dividing xi to power j minus 1. So we get the solution as xi equal to 1 and 1 minus kh. So the solution finally will be uj equal to a1. First solution is exactly same as the analytical one, and b1 into 1 minus kh, and we'll try to see that how it will behave. So for k greater than 0, let us take that kh is less than 1, and I mean this quantity is greater than 0, and then you see that uj behaves exactly like e to power minus kx, because it is very obvious, nothing is there to say. So e to power minus kx goes to 0 as x approaches to infinity for k greater than 0. Similar behavior you see here also, so there is no difference. And similarly, you can see for k less than 0, 1 minus kh. So exactly the similar way. And then for large k, 1 minus kh goes to minus infinity, and as k approaches to infinity, so this will always oscillate. There is no doubt that minus 1 to power j into infinity, we cannot control that as k is very, very large, and so it always oscillates. So it is not possible to find the solution for this case. Is that right?
Yes, sir.
So this is the total analysis of your stability part, and the next part I will start on Saturday, not today. If any query is there, you can ask me. Anybody? Anything you want to ask? Anything which is not clear?
No, sir.
Okay. So then I will close at this stage. and then we'll meet on Saturday. Okay?
Thank you, sir.
Okay.
Thank you, sir.